Hey guys, so instead of allowing our bike to get damaged and trying to understand how this permanent damage has been brought about, what we are trying to do in these series of discussion is we want to rather increase the hardness or this hardness of our bike to the extent that when someone wants to damage it, it is able to withstand. So particularly we are focused on the rim of our bikes, and our goal here is not to let this rim get easily damaged. So in order to achieve that, assuming that our rim is made up of steel, we place our rim in a carbon rich environment, raise the temperature of that environment and hold it for a prolonged period of time. This allows the influx of carbon, thereby increasing the hardness, and that is what we are trying to do. Now this entire processing, we want to put it in a mathematical framework, and we saw in our previous discussion that when we have such a system where there is a disparity in carbon concentration depending on the position I take, there is a flux that is going to get introduced wherein my carbon is going to move from a region of high concentration to that of the region of low concentration. So in our specific case, my environment is a carbon rich region and my steel rib is a carbon deficit region. So since I have a inhomogeneous distribution of carbon concentration, meaning depending on the position I take, my carbon concentration is going to vary. As I increase the temperature and hold my system for a prolonged period of time, my carbon moves from the region of high concentration to that of the region of low concentration so as to reduce the entire inhomogeneity. Now, this mathematically, this movement, this influx of carbon from that of the rich surrounding to that of the deficit region of interest, this movement of carbon is what we refer to as diffusion, and this influx of carbon is rather described by this law here. So this is what we refer to as the Fick's first law of diffusion. So this movement of carbon, we refer to it as diffusion, and this expression here that describes how this influx of carbon or what governs this influx of carbon is what we refer to as the Fick's first law of diffusion. And what this expression states is the influx of carbon depends on how my carbon concentration is changing with respect to my x-axis, y-axis and z-axis. So how my carbon concentration is changing when I change my different position, and the way I quantify this change in carbon concentration is I consider my change with respect to x, I consider my change with respect to y, and consider my change with respect to z. Now that dictates or that governs my flux of carbon. So that is what this first law states. But what critical aspect we understand is this way of describing the difference in the carbon concentration with respect to position, we refer to it as gradient. So essentially we are describing how my carbon concentration is changing with respect to my position. The way we do it is we consider the change in carbon concentration with respect to x, how it changes with respect to x, change in carbon concentration with respect to y, and change in carbon concentration with respect to z. In addition to that, we are introducing the corresponding unit vectors of x, y and z. So this is responsible for what, or this is what governs our flux, that is J. So what it means is, even though I use this expression to quantify, to express the change in carbon concentration with respect to position, it also tells me that the resultant is going to be a vector, the flux is going to be a vector, and it is going to point at this ijk direction. It's going to point at this direction of the vector. So in addition to describing the change in concentration with respect to my position, by introducing the corresponding unit vectors, I am in a position to tell in which direction is my influx of carbon atom is going to be. So this is possible. So this is made possible for us by this operation, by we considering the gradient of concentration. So put it all together, what gradient helps me understand is how my carbon concentration is changing with respect to my different directions, and the overall resultant flux is going to be in a specific direction, and like we saw in our previous discussion, this direction is going to be the one wherein there is a significant difference in the carbon concentration. So what the gradient tells me is how my concentration is going to change with respect to my x, y and z, and by associating the corresponding unit vectors, I'm now able to associate, or now I'm able to give a specific direction to to the flex that is going to get introduced. Now what ultimately this formulation, this first law helps me understand is what is responsible for the spatial change in my concentration. Now when I have an inhomogeneous distribution, this expression here tells me there is going to be a flux that will be introduced, and flux is going to proceed in a specific direction. So ultimately there is going to be a change in the carbon concentration when I change my position. So the change in the carbon concentration with respect to my position is responsible, or this is being achieved by the flux here. Now as we considered in our previous discussion, my concentration is just not a variable that is dependent on my position. It is also a variable that is dependent on my time. So it's a spatio-temporally varying parameter. So my flux helps to understand how with respect to my position, my concentration is going to change. Now I want to understand how with respect to my time, my carbon concentration is going to evolve. So that is one other piece of puzzle that I need to address. The Fick's first law says there's going to be a flux that is going to change the concentration at different position. Now I need to know how with respect to time my carbon concentration is going to evolve. Now that is rather given by the Fick's second law. So what Fick's second law states, or the mathematical description of it is, it helps us understand how my carbon concentration is going to change with time. So this is what my Fick's second law helps us understand. And as you can see here, this Fick's second law, it takes the dot product of this nabla to that of the flux. So what it essentially does is, it is ultimately considering, or ultimately it includes the dot product of a vector and an operator. And this operator nabla is something we saw in the context of the gradient, and this nabla we write it as change with respect to x, including its unit vector, change with respect to y, including its unit vector, and change with respect to z, including its unit vector. Now when I consider the gradient of my concentration, I end up having something like this: change in concentration with respect to x with its unit vector, change in the concentration with respect to y with its unit vector, and change in my concentration with respect to z and its unit vector. So this I get from my Fick's first law. So this is rather the portion of my flux. And this, in case of the Fick's second law, I'm taking the dot product of this guy and this guy. I'm taking a dot product of these two. So ultimately what I would end up having is a scalar, and the scalar would be expressed as something like the double derivative of my concentration along the x, my double derivative of my concentration along the y, and the double derivative of my concentration along the z direction. And this is how my concentration is going to get, or how my concentration is going to evolve with time. So the Fick's first law tells me the introduction of flux. The Fick's second law gives me this expression, which is arrived at by considering the dot product of this operator to that of my gradient here. So this gradient gives me flux, and when I take the dot product of this operator to that of my vector, that is flux, I end up having this expression. I end up having this leads to this, and this ultimately governs how my concentration is going to change with respect to time according to my Fick's second law. So this is going to be a scalar as I'm considering the dot product here. Now basically what I then end up having is, I now know how my concentration is going to change with respect to my space and also with respect to my time. So this is what governs my change in the concentration with respect to my space and with respect to my time. So ultimately when I'm able to solve this, I would be able to arrive at an expression that tells me what will be my concentration at a given position and at a given time. So ultimately I now have an expression. This expression, when I solve it, I'm going to get a parameter that, or I'm going to get a relation that will help me understand what is going to be my carbon concentration at a given position and at a given time t. And we have already seen that it is hugely relevant to us, because using this we will be able to plan the entire process of increasing the hardness of my rim. So therefore, considering this expression here and solving it and arriving at this relation here is hugely helpful to us, because it's going to help us in the real world to plan a process wherein I can do something about my material. And that's the reason why it is rather helpful for us to consider this and solve this, or relevant for us to consider this expression and solve this expression. Of course, this here can be written as, this expression here can be written as square of my concentration. So this is rather the shorthand notation of writing this. And basically, when this is called as the gradient, this dot product, when you're having nabla and taking the dot product, this combination is what we call as divergence. So what you do is, you take the gradient of a parameter that changes spatially, you end up getting a vector. In case of divergence, you take the dot product of the spatial change with respect to a vector of a vector, you end up having a scalar. So divergence, the gradient gives you a vector, whereas divergence, by considering the dot product, gives you a scalar. And in our case, it is the divergence that dictates how my concentration is going to evolve with time. Now in this lecture, what we will do is, we will try to take the analytical route of solving this expression here. Now we have an expression, we have this expression, and this expression, when we solve, we are going to get a relation that will help us understand how our concentration is changing with space and time. Now in this lecture, at least even if you are not rigorously solving it, we will try to see what is the approach to solve it, or when we want to do it analytically using pen and paper. Now one objective of this discussion here is, we want to differentiate the analytical solution from that of the numerical solution. We want to approach a given numerical problem, we want to see a given expression, and we want to consider two different ways of solving it, and we want to understand what is rather the advantages and the disadvantages of taking one approach over the other. So this is one other objective of our present discussion. We have a numerical expression before us, we want to solve it. There are more than one ways to solve it, but as far as the categories go, there are two different categories of solving it. One we call it as analytical, the other we call it as numerical. We want to understand these two. So that is what one of the objectives is going to be. To start off, we will try to solve this analytically, meaning we will try to use no complex, or we will not use any help from the computing machines. We will try to solve it using our pen and paper calculation. So fundamentally what we have is, the key difference from all the expressions that we have solved so far to that of this expression is, this expression is no longer an ODE, it is a PDE. From our previous sessions, it is safe to say that we know how to handle, at least if we see an ODE, at least we will be able to classify it, we will be able to think of some techniques on how to handle our ODE. So this ODE, handling ODE, we are fairly, I wouldn't say comfortable, but we can manage, we can tolerate ODE. But PDE is totally different ballgame. So what we essentially want to do is, when we want to solve this PDE using pen and paper, we want to do it based on our understanding. This is possible when I'm able to translate my PDE to an ODE. If I'm able to translate my PDE to an ODE, then it should be possible for me to solve this expression here. Alright, because in our previous session we have seen how to handle ODE, how to get acquainted with ODE, how to tolerate ODE. So when I'm able to then translate my PDE, the PDE that is before me, that will help me understand how my concentration is going to change with my position and time. If I'm able to translate that to an ODE, then I will be able to solve my ODE and ultimately get a relation like this. So that is what we will be doing. If I start that derivation now, it's going to make this lecture rather prolonged. So with this outline, we will start the upcoming session.